we're going to finish up talking about the atom and then go to nuclear physics, which is actually more about the atom. So where we've covered so far is talking about the periodic table, the periods and groups down to that point. So we're going to start talking about identifying atoms using the spectroscope. So I'm going to start first off by doing this. So I'm going to pass out these glasses. I want these glasses back. Please don't write on them. I've had a few students who have written on them. These are called diffraction grating glasses. They are glasses that have a whole bunch of little lines on them, essentially. And when you put them on, you see cool things. So what kind of things do you see with these glasses on?
Oh, other than rainbows.
Okay, you see like rainbows. And you can see really cool effects. Like if you look at the lights, if you look at lights that are off their distance, not the ones directly above you, you'll see what looks like different layers. And actually from where I am, if I look at the papers that the students have on their desk, I see like 3 sheets of paper for every sheet of paper. But they're different colors.
Ooh, yeah.
So, what are these glasses doing?
Looking at the light layers.
They're doing what?
Looking at the light layers.
Breaking up the light layers, she said. Well, what?
Nothing.
Nothing?
No. I said they can see the little light particles, like the colors.
Light particles. Well, what the diffraction grating does is really interesting. When light goes around a corner, it bends. Probably never think about light bending, but it does when it goes around corners. The same as sound does. If I go outside the door and have the door open, I can talk from out there and the sound waves will bend around the door and you'll hear me in here. Light, you can't see me if I'm around the corner. But the light waves do bend, they just don't bend enough for you to see me. But with these glasses, with these little slits really close together, we see different colors at different angles. And so it's separating so we can see the different colors individually. So when you look at that sheet of paper and you see distinct layers, I see, looking at the paper in front of Ashton right now, I see a distinct strong green layer. I see a distinct strong red layer. And if I look at the lights, I'll see something similar. When I look at a light that's back there, I see a green layer and a red layer and a blue layer and a yellow layer, and there's one more layer in there. I see those layers because the lights are putting out specific colors. They're not putting out one color that's white. You know, you look at them without the glasses and it looks white. You look at the paper and it looks white. But that's actually a bunch of different colors mixed together. They're distinct colors. So now instead of looking at those lights, we're going to look first at an incandescent light to just get a little better idea of what the glasses are doing. And then we're going to look at what comes from a single type of atom. So turn this on. Right now it's not giving off any light. And turn off all my lights. Don't worry, it'll turn off. And I have to turn off the projector as well. The door we're just going to have to deal with. Okay, so I'm going to turn this on just a little bit. Now, if you look just at the filament, what color would you say that filament is?
Orange.
Okay, orange is, I think, the dominant answer. But if you look off to the sides with the glasses, you should see some colors. And what colors do you, well, they're actually, because of the way the glasses are made, you're going to have 6 of them, I think. But what do the colors look like?
Green, yellow, red.
Okay, green, yellow, red. Don't see blue, do you? But it's continuous. All the colors are just smoothly going from one to the next. If I make it hotter, the first thing you notice is it's brighter. Second thing you notice is the color is a little brighter. The color is closer to white. So the light is brighter and the color is closer to white. And now if you look at the rainbow stuff, you see just a little bit of blue.
Yeah.
Keep warming it up. Gets much brighter. The brightness is the amount of light that's giving off is proportional to temperature raised to the fourth power. So if you double the temperature, it's going to be 16 times more light.
8 little big ones.
And yeah, 8 actually. I could only see 6 when it was lower intensity. Now I see 8. The reason it's 8 actually makes sense because this has lines this way as well as this way. And so if you had lines only one direction, you'd have 2. You put the other direction and you get 2, but then you have to double the others. And that's what gives you the 8. Okay, so now you can definitely see some blue, and I'm going to continue to make it hotter and watch what happens to the color. Now you'd say the color is white, and you see blue as well as violet. Now, technically it's not purple. Purple is mixing red and blue. Violet is just a single color. There's a difference. We didn't talk about colors when we were talking about waves, but violet is a mixture of 2 different colors. Purple is a mixture of 2 different colors, and violet is the one single. So when we make this really hot, it has all of the colors in the rainbow, and we call this color white when we're mixing it all together. So this is what happens just when you make something hot. We call it incandescence. This is how things like your car's headlights work, the standard light bulbs that we used to use in our houses work. Now I'm going to shift from the incandescent light to using a single gas. So here's a single gas. I got to turn this off. And now if you look at this, you should see what color does it look like at the main filament. Personally, I'd go with pink. And then if you look off to the sides, you see a bunch of colors, right? You should see a violet, and then there are 2 that are in the blue-green range that are very, very faint. You may not see those. There's one that's a bright green, one that's a bright yellow. There's a faint yellow. Then there's a whole bunch of reds. I can see about 8 or 10 reds. Now I'm closer, you may not be able to see as much, although you probably have better vision than me, you might be able to see all that I described. Those are very specific colors of light. There's only certain colors here. It doesn't matter where you are. If you look at this kind of gas, you're going to see those colors. So I'm going to change now to what I think is a different kind of gas. Notice the color has changed to this. It's not pink anymore. It's just kind of blue. And that's because it's warmed up. And so the colors that we see out there that are making it up will have also shifted because of that. That is, you'll have stronger ones that were weak before. Okay, so let's change to a different kind. I think it's a different kind of gas. If it's the same gas, I'll just move on. As Mariah can attest to, I didn't spend too much time looking at these before class. Okay, that's definitely a different gas, right? When you look at the colors, are they the same colors off to the side that you had before? It's a different set. Each gas has a distinct different set of colors that it will produce. So we can differentiate from one type of gas to another type of gas by looking at the spectra of colors. We call it the spectrum when we break out and see all the different colors. But by looking at the different colors that it produces. So that's what spectroscopy is. Spectroscopy is looking at the different colors that are being produced to identify what's going on. And notice this one here has a super bright yellow. And the color here is kind of, I don't know, let's call it peach. So I'm going to turn on the lights now just so you're prepared and not all shocked like, what? Wrong ones. The ones so you can see. Now do remember, please, to give me these back at the end of class. I don't think they do. It's not like I pay super close attention because I trust the students, you know. So what we looked at was the spectrum, the different colors that the elements emit. And you can think of them like a fingerprint for the elements. If it's hydrogen, it's going to have this specific spectrum. If it's helium, it's going to have this specific spectrum. And different gases will have different spectrums. And in the 1800s, people noticed that something like hydrogen has a very ordered spectrum, and Johann Balmer came up with a mathematical equation to describe the wavelengths. And so the equation that Balmer came up with is so that was Balmer's equation. 1 over the wavelength. Now, what's the wavelength? We've talked about this. It's something that will be on our test that's coming up. So what is the wavelength? That's the period. Period is the time it takes to repeat. The distance it takes to repeat. And wavelengths of light are measured in the nanometers. What does nano mean? Okay, we often say tiny because it's used commonly to mean small. Nano means 10 to the minus 9. It means 1 billion. So they're measured in the billionths of meters. Something like red light is in the range of 600 nanometers for its wavelength. Anyway, this equation, where R is the Rydberg constant, named after Johannes Rydberg there, gives you the wavelengths that you see in the hydrogen spectrum. And we call those the Balmer lines because Johann Balmer is the person who gave us this equation. But it's kind of funny, just historically. As equipment got better, people developed equipment that could see ultraviolet radiation. And when they saw that there was ultraviolet radiation, they saw, hey, there are more lines here in the ultraviolet spectrum. And so Lyman, I don't know Lyman's first name, came up with his own equation that said, well, those ultraviolet lines are matched by this equation. I put 1 over 1 squared, which is always going to be 1, just like 1 over 2 squared is always going to be 1/4. And so I said, this equation will give us all of those ultraviolet lines. And then as they started to be able to detect infrared radiation, they saw that there's more lines in the infrared. And we have other people, let's see, there's, Lyman, Balmer, something, Brackett, and Fund. And I can't remember what the other one is, but different people came up with different equations. So if you put them all together, you just have 1 over wavelength is equal to this constant times 1 over n1 squared minus 1 over n2 squared, where n2 is an integer bigger than n1. And so N1 is the number that identifies the person who came up with the line series, you know, Lyman, Balmer, whatever, Brackett, Fund. And N2 is some integer larger. So they had this organization, mathematical set of equations to explain, or not to explain, but to predict what the wavelengths would be. Scientifically, that's really unfulfilling because scientists, the whole point of science, you find something interesting, you come with a hypothesis that explains why that interesting thing occurred based on scientific information, makes testable predictions. This here was just an equation. Now the equation makes testable predictions, but there's no explanatory. There's no explanation as to why they're there. And so that's problematic for scientists. It's something that you want to study. And so studying it, by the way, here's pictures of the spectra you see if you look at different elements. So there's strontium spectrum, potassium, barium, copper. They're all different spectra, which give you combined different colors for the material when it's in a flame. And it was Bohr, Niels Bohr, with his Bohr model of the atom. Remember the Bohr model? He said the electrons are doing circular orbits around the nucleus with only certain angular momenta possible, which resulted in only certain energy states possible. And he said that the lines we're seeing are occurring when an electron falls from a higher energy state to a lower energy state. If it falls down, it's giving up energy. The example I used last class period, I dropped that stopper thing. When it hits the table, it gives off sound. That's from the energy coming out. Well, he said the energy in the atoms is so high that when an electron falls from a higher energy level to a lower energy level, the energy it gives off, instead of being a sound wave, is going to be a light wave with energy that could be in the visible spectrum. And so according to the Bohr model, your electrons can have only certain energies. So energy is on this axis. Up here is 0. Down here for hydrogen is minus 13.6. The units we use are electron volts. Don't get hung up on the electron volt. It's just a unit for energy. So we have a negative energy. And these, remember I used that number n? N equals 1 is the bottom energy state. N equals 2 is the next one. N equals 3, N equals 4, and so on. And they get closer and closer together because according to the Bohr model, the energy is minus 13.6 electron volts over N squared. Well, here's the beautiful thing. The Bohr model has a scientific background for how he came up with this. So that energy equation is a scientific idea. And with that scientific idea, if the electrons are falling from one energy state to another to give off light, then you have, for instance, an electron falling from here to here has an energy difference of it's minus, and it's going to be the final state. Minus the initial, I should have put it this way. The final state was n equals 2. The initial state was n equals 3. And so that's what you would get for the change in energy. Now notice there's a minus sign out front because you had a minus sign in the energy equation. And then you have 1 over 2 squared, that's 1/4, minus 1 over 3 squared, final minus initial, 1/9. The energy is going to a lower value. That's the energy of the electron going down. That change in energy has to go off in the light. And so the light comes off is equal to minus that delta E. So that's going to be 13.6 electron volts times 1 over 2 squared minus 1 over 3 squared. But if you look at the Balmer equation, that would be one of the Balmer lines because the first thing is 1 over 2 squared. That's what Balmer had for his series. And so, in fact, any electron that falls from a higher energy state down to n equals 2 is going to give us one of the lines in the Balmer sequence. So now we have a scientific explanation for what was going on right here. So what we saw, right, we saw that there were specific lines. Now we have an explanation for it, and for the hydrogen atom, Balmer was able to calculate what the energy should be, and they matched up. Well, that's making a testable prediction, calculating what the energy should be, and then testing it, and they agree. So there's a good reason to believe Bohr's model. Except for there were some problems with Bohr's model, like I said, and things have moved on to the quantum model. But the calculations for energy for the Bohr model are, the starting point is the same as what you get with quantum physics. With quantum physics, you add some more difficulty to it that causes little variations to answer the questions that the Bohr model wouldn't. But we have scientific experimentation that confirms some of the predictions of the Bohr model, and the scientific method, the things that aren't confirmed, then you modify the model, you modify your hypothesis to come up with a better one. That's how we ended up with the quantum one. So what's the really important take-home thing about this? You saw that we have very specific colors that are present in the gas. And now we have a scientific theory that explains why we should have those specific colors. So we go from, wow, that's something miraculous, to, yeah, we can understand why we should have those specific colors. Because the electrons can only have specific energy levels in an atom. And when the electron falls from one energy level to another energy level, the difference in energy is given off as light. Now, this picture has two pieces. I've only focused on this one. This is electron dropping in energy, going to a lower energy state. On the other side of the picture, there's an electron rising in energy. If it's going to rise in energy, something's going to have to give it energy. Where does it come from? It comes from light. You can also give it energy by collisions, by the way. But typically we talk about light. And so the left picture there, the electron rises by absorbing energy that's exactly the energy difference between states. So if you shine light through a gas, it will absorb only the specific colors that have the energy difference that matches your gas. So the absorption spectrum, the lines, the colors that would be absorbed by gas, are exactly the same as the emission spectrum, the colors given off when you excite the gas. Because it's just electrons going up if you're absorbing, going down if you're emitting. Question?
I was going to ask, so what you're saying is that when there's different, the reason why different lights were emitted has to do with different energy levels?
Yes.
Okay.
And so they, let's take, going back to the hydrogen atom. The hydrogen atom with a picture like this, it turns out that if you have something falling down to the lowest energy state, the Lyman series, the energy is so high that it makes ultraviolet light and we can't see that. And if it's falling down to n equals 3 or above, then the energy is so small that it's infrared and we can't see that. So the only ones we can see with our eye are the ones falling down to n equals 2. That's why the Balmer series was the first one identified, because only if they're falling down to the second energy state is the energy in the range that makes visible light.
So then some colors have higher energy levels than others.
That's right. And in fact, the equation for that is energy. Let me change colors. The energy is equal to H times the frequency, where H is 6.626 times 10 to the minus 34 joules times seconds. And so we call the little piece of light a photon, and that's the energy of a photon. It's the frequency multiplied by that constant.
So the photon's being emitted, is that how the color comes into place?
Yes, the color of the photon depends on its frequency. And since you only have certain energies, that means you only have certain frequencies, and thus only certain colors. Okay, first of our clicker questions. The hydrogen spectrum, and you can answer now. I think I might have found a way to get around the problems we've been having. We will see. The hydrogen spectrum consists of many spectral lines. How can this simple element, hydrogen has one proton in the nucleus, one electron orbiting it, have so many lines? I was worried something was wrong since there were no answers for a while. Now that they're coming in, I breathe a sigh of relief. Okay, still waiting on Mariah. Mariah? Still waiting on you. I don't have an answer from you yet. Oh, okay, there's it. For some reason, has forgotten who you are again. Okay, so we have. So yes, you had answered. I just didn't see it because it. 6011. So we had fairly good agreement there. 6 people said one electron can be boosted to many different energy levels. That's correct. That's what we were seeing here. We have all of these energy levels that the single electron can have. And so any jump from one energy level to a lower energy level is going to give off light. And so we can have lots of different colors produced because there's lots of different levels you can jump between. Okay, the quantum hypothesis. The quantum hypothesis is actually here talking about light. Max Planck, was trying to explain the radiation that we see from this light bulb. Remember when it was cool, we didn't see any blue and it looked orangish? As it got hotter, it looked more white and we saw that there was blue and violet added in. Well, Planck was trying to explain how you got those colors that we were seeing. And one night he got a telegram that said at really low temperature, the emission varies like this. I don't remember what the telegram actually was. And he wrote out a postcard and said, well, if that's the case, then this equation should fit the data. And it did. Now, to me, that's like super genius to just take this one little piece of information and say, wow, here's the equation. But once again, he had an equation without a scientific reason for it. To a physicist, that's like failure, you know? I found it's like on a test, if you get the answer right but you don't know why, you have no surety that when it comes to get on the final exam, you'll get it right? There's a certain failure even though you got the question right. And so Planck studied for, I think it was 6 months, 9 months, something like that. And he said, wait, if the light comes off only in certain packets of energy, then I can give a physics explanation for why my equation is correct. And so that's the quantum hypothesis, saying that light comes in units, packets that we call quanta, with only specific amounts. It's like you can be on the first step of a stair or the second step of a stair, but you can't be some arbitrary amount between them. You can only be on one step or another. That's what it means for something to be quantized. You can have 1 cent in your pocket, you can have 2 cents in your pocket. You can't have 1.3 cents in your pocket, right? There is no option for that. And so he said, if the light comes out in 1 packet or 2 packets or 3 packets, but nothing in between, then I can explain with physics why my equation is right. And so his was kind of a, if this occurs, then I can give you a physics explanation. And Albert Einstein, who at this point was working in the patent office, getting his kicks by going to the pub at night with his friends and talking about the most recent papers in science, Einstein wrote papers. He wrote 3 papers in 1905, and each one of them, well, he might have written more, but he wrote 3 really pivotal papers in 1905. And one of those papers was on a theory of special relativity. Special relativity means the easier part. That's the one that most people think of him as being famous for. You know, you've heard E equals MC squared. That's part of that paper. He wrote another paper to explain Brownian motion, which in a biology class you might have heard about Brownian motion. Brown was looking at pollen grains that were floating on water through a microscope. So he looks through his microscope and he sees these pollen grains vibrating in the water. And he was like, well, what would make them vibrate? We don't have Parkinson's. It must be the result of some cavorting beasties, some kind of microscopic animal life that was bumping it, was his explanation. And Einstein in his paper said, no, that's because of the kinetic theory of nature. That is, temperature means that the things are moving. Only if the temperature is absolute zero are they stationary, which is not possible. And so the things are moving, and so the water molecules are moving very quickly. And when the water molecules hit that pollen grain, it's so light, it has such a small inertia that when it gets hit, it will respond very easily. And so you could see the collisions with water molecules hitting the pollen grains. And then there's his third paper, the one for which he and Planck and Einstein both got Nobel Prizes for this. And his third paper was on the photoelectric effect, which was a paper that says that light behaves as a particle. And that particle has energies for the particle. That is the equation I showed you, E equals HF. That particle is called the photon. Nice. So the energy of a photon is the h times frequency, where h is that Planck's constant named after Max Planck. And so Planck came up with this quantum idea, and then Einstein was the one that says, yeah, that's right, and gave an experiment to predict it. Now that brings us to something really weird. What is the nature of light? When we studied waves, I said light was a wave. How many people remember me saying light is a wave? Okay, good, because we do have a test that's on Friday. And this is, that's some of the materials on the test. If we were to go back historically, Isaac Newton said that light was a particle. Isaac Newton said that light is like BBs, and he explained much of optics by treating light like BBs, particles. But then it was Thomas Young who did experiments with double slits, experiments with something like the glasses you use today, that showed that light bent around objects, which doesn't make sense if it's particles. BBs don't. You have a wall here. It either hits the wall or it misses the wall and just keeps going straight. That's what particles would do. But waves would bend around, like ocean waves will bend around up here. And so Thomas Young convinced everyone that light was a wave. And then you wait, roughly 100 years, and Einstein comes back and says, yeah, Newton was right, light is a particle. But they already had an experiment that disproved light being a particle, because particles can't bend around objects. If you're a scientist, you have a theory that disproves that light is a particle, but now you have a new theory, and there's an experiment that's called the photoelectric effect that Einstein proposed, that people did, that disproved that light's a wave. So we can disprove that light's a wave, we can disprove that light's a particle. What do? That's what scientists came up with. They said it's both. It's both a wave and a particle. Sometimes you see the wave nature, sometimes you see the particle nature. To me, that's very unfulfilling. I want it to be one thing. And so I believe that there's still something to be learned here about the fundamental nature of light, how it really works, because the whole dual nature thing is just unfulfilling to me. Question?
So I have a question. So if I'm going to examine, if you asked what is it and it only had photons but didn't have waves anywhere, would that be the right answer, or would it be like wrong? It's both?
It would have to be worded correctly. It would have to be which is consistent with the nature of light, and you would have a wave, and you say, well, a wave is consistent with some of its, or say which is consistent with some of the behaviors of light, and then you could say wave. Right? It has to be worded right.
Some of the waves.
So it's not, so it's not exclusive.
Okay.
And so here's the simplified version. That little tilde, that means is proportional to, it's a way, it's not normal proportionality symbol is this, but it's saying the energy of the photon is proportional to the frequency. And so then we have Niels Bohr, the work I've already talked about. And so I can skip right over this because we've talked about all of these things already. With Bohr's model, the electron's energy state, well, it was their angular momentum state is what is numbered by n. With the quantum model, the n does number energy, so we just talk about it as if Bohr said n numbers the energies. So the energy states are numbered by the n, and that was where we had the equation I gave you that energy is equal to minus 13.6 electron volts over n squared. That's only true for a hydrogen atom. If it's a helium atom, then you have to put the number of protons in the nucleus. Z is the number that tells us the number of protons in the nucleus. What's the name for that? What's the name for the number of protons in the nucleus? Yes, the atomic number. So Z is the symbol for the atomic number. The energy is minus 13.6 electron volts multiplied by the number of protons in the nucleus, the atomic number squared, divided by n squared, where n is the energy state. And so that's what we use as a starting point for any type of atom. It gets more complicated, but we don't need to go more complicated. Now, one last thing here. According to the Bohr model, the electrons did circular orbits. Louis de Broglie, actually you want to pronounce it right, it's Louis de Broglie. B-R-O-G-L-I-E is Broglie. Louis de Broglie came up with the relationship between wavelength, the symbol for wavelength is lambda, and momentum, which we are not going to study at all. But his theory saying that electrons going around the nucleus have a wavelength actually exactly matched the outcome of Bohr's model if you said that the electrons are making complete number of cycles as they go around. So an example is shown here using actually Pasco equipment, I believe. Does that look like Pasco to you? Yep. Paul A. Stockstead Company right there. Let's change to a color you can see. Pasco. This is just a piece of wire, and then they're vibrating the wire, and you can set up what we call a standing wave, where it goes through, this is 1/2 cycle from there to there, another half cycle from there to there, and there. So it has 3/2 wavelengths is equal to the circumference in this picture. And that's the only pictures we have. The others aren't setting up resonance. If you have the frequency right to make the wavelengths an integer multiple of 1/2 wavelength for the circumference, then it will set up a standing wave, and that corresponds to the Bohr model's predictions of the energy levels. So this here is showing an example of so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 half wavelengths if I started and ended the same place. And so that would be the n equals 10th state. And if it doesn't have an integer number of half wavelengths, no go. All right. This is the last picture for talking about the electrons before we move to the nucleus. According to the Bohr model, we had spherical orbits. The pictures are drawn as per the Bohr model, even though with our quantum model, we know they're not spherical shells. But we talk about the energy levels as being these spherical shells with different radii. And so when we look back there at the periodic table, the periods are telling us which shell we're filling. And so the first period is the innermost shell. And the second period is the next shell, and so on. Now the numbers it shows here, 2, 8, 8, 18, 18, 32, 32, those are the number of electrons, well, the number of elements you have in each period. there is some confusion because, as I think I told you, in the fourth period, going from scandium to zinc, those are actually filling electrons in the third shell instead of the fourth shell. But for your level, we're just considering that as if it's in the fourth level shell because that's where you're filling it. So when we talk about the shell model for an atom, we're talking about there being different energy shells corresponding with the different periods that the electrons go into. Now we're going to shift to talking about, oh, yeah, I thought that was the last one. Here's pictures showing the electrons with the shell model. So for hydrogen, it's 1 electron, it's in the first shell. Helium, 2 electrons, still on that first shell. But 2 is the maximum number of electrons that will go in the first shell. So if you have 1 more proton, you have 1 more electron, and lithium has 2 in the first shell and 1 in the second shell. Beryllium has 2 in the first shell, and then if you look carefully, 1 there and 1 there, 2 in the second shell. Boron, 2 in the first shell, 1, 2, 3 in the second shell, and so on as you go across. And then the third, doing the same thing. So that's what the shell model is saying, that you're putting the electrons in. If it's in the first period, you're putting them in the first shell. Second period, you're now adding electrons to the second shell because the first shell is complete. And remember, these things over here are stable because they're completely filled in their shell. There are no more electrons that can go in that shell. That's what makes them so stable. That's why they're inert. The halogens are 1 electron short of having a full shell. So they really want another electron to get to a full shell. And if you go over to the alkali metals, these guys have 1 more electron than they would have in a full shell. They don't care so much about that extra electron because they liked having the full shell. So that's some basics of the periodic table. Any questions on the periodic table before I move to the nucleus? None? All right. So now we're going to talk about the nucleus and radioactivity, which is totally, well, of course it's physics, so of course it's fun. I know we're in the chemistry section, but it's still physics to start the chemistry section. So we have to talk about what is radioactivity. Here's somewhat of an example of radioactivity. Treat the nucleus like this pencil in my stopper. It's pretty much stable, right? Because the pencil's not falling out. But if I shake this a little, okay, shake a little more, the pencil falls out and it fell down to a lower energy state. That's what's going on when you have a radioactive nucleus. The nucleus has an energy, and it could be in an excited state, a state that's kind of stable, but with a little bit of shaking, it'll fall to a lower energy state. And when it falls to a lower energy state, just like the electrons gave off light when they fell from a higher energy state to a lower energy state, the nucleus gives off energy when it falls to a lower energy state. But the energy in the nucleus is really high. And so when things fall from a higher energy state to a lower energy state, they usually are a big change in energy. So the energy that comes out of the nucleus tends to be really large. And so when we're talking about radioactivity, we're talking about the nucleus of an atom going to a lower energy state and giving something off. That something off could be a number of different particles. And so we'll have to talk about what those are. Notice that statement, radioactivity has existed longer than the human race. That is, radioactivity has existed for as long as there have been, well, I should say atoms per se, but something like that. And I don't care who you are. I don't care what your belief is about creation. Even if God created humans only 6 days after he created the entire universe, for those 6 days, you would have had radioactivity but no humans. 6 days on the 6th day and created man, right? So radioactivity did exist longer than the human race, and depending on your worldview, that could be for an additional 5 days, or it could have been for whatever the period was from when God created the heavens and earth to when God created, the light to rule, or created light on the first day of creation. Or if you don't believe in creation at all, then, well, from the time when the Big Bang occurred until the time when life first formed. So, what makes a nucleus unstable? We'll go back to the shell theory. I don't think I have this. Yeah, I don't have it here. But I'm going to talk about the shell theory. So it's not in the slide. There's nothing there about what I'm talking about. Maria Geppert-Meyer. She was an American physicist who had the misfortune of her husband also being a physicist. Why would that be a misfortune? Don't ask Amy. She'll give you lots of reasons. In her case, it was because of anti-nepotism rules. Y'all know what nepotism is? Okay. Nepotism is when you hire family members, giving them preference over other people. And so you can look at our White House today, and you have Donald Trump has his advisors are like his daughter and his son-in-law. And while they're not getting paid for being the advisors, I don't think, and that's how they get around nepotism laws, it's still, in most people's view, something with nepotism, something not good. Well, in Maria Geppert-Meyer's case, her husband worked at the University of Chicago, and she wanted to do research too, and they basically said, well, we'll give you an office. You can come on in and do stuff. We just won't pay you because we're already paying your husband. And so she's here working gratis for free, and she came up with a shell model for the nucleus, saying that the nucleus of an atom has energy shells, just like the electrons had energy shells we talked about. And so she said, if you have, for instance, 2 protons, that's going to be more stable. And if you have 2 neutrons, that's going to be more stable. 2 neutrons and 2 protons is together really, really stable. And then other combinations aren't as stable, but if you fill the shell, it'll become more stable. And so she came up with this model, the shell model for energies of the nucleus, to help explain the stability of some atoms and the instability, the radioactivity, in others. A very funny historical point of view, or point. She came up with this theory during the Cold War. The Cold War, which is actually the time when I was growing up, is the time when the United States and Russia had finished World War II and were now kind of viewing each other as potential enemies, and they were trying to compete with each other without actually going to war with each other. And yeah, don't put Cold War in your potential test question. And so in the interactions, people thought about war. And so she writes a paper about the shell theory for the nucleus, and the people who translated her paper into Russian translated shell as the word grenade. You pull the pin and the grenade's no longer your friend. And so they thought she was talking about something like a hand grenade is what the nucleus is like. And this caused the Russian researchers to be behind Americans simply because that word was misinterpreted because of the state of relations between our countries at the time. And so now we understand that the nucleus has energy shells, something like the electrons. Our understanding is not very complete about those shells, by the way. Now, radiation. I talked about nuclear radiation, not the only kind of radiation. Light that comes from your body because you are not at absolute zero is also radiation. None of us worry about damage from the radiation coming from another person. Most of us don't damage about the radiation coming from these lights. Some people do worry about the radiation coming from our cell phones. The cell phones are emitting some pretty strong radiation. Usually the only radiation we really worry about is radiation that has the potential to harm our bodies. Radiation that has the potential to harm our bodies, well, right now the sun is bombarding us with particles. One kind of particle is called a neutrino. The neutrinos, the neut means neutral. They have no charge, just like a neutron. The eno is diminutive suffix, meaning they're really tiny. Since they're really tiny and have no charge, they go through us. They will not cause you any damage. So nobody worries about the neutrino radiation because it can't harm you. It just can't. It's going through you right now, millions of them a second. Not causing you any harm. It goes through the earth, keeps going. At the same time, we have protons and neutrons that are coming from the sun. Now, the protons are largely deflected by the Earth's magnetic field, so we're not getting too much proton radiation from the sun. If you go closer to the poles, you'll get more proton radiation from the sun. The neutrons, they're neutral, but they're large enough that they do have some bit of health risk. And then there's, of course, the visible light coming from the sun. That visible light, we have visible light all around us. We don't tend to think of it hurting us. But we do know that if you suntan, that can lead to skin cancer. Why? Because the ultraviolet light that's coming from the sun, that's also radiation from the sun, has a high enough energy in the photons. Remember, E equals H times frequency? The ultraviolet light has a high enough frequency that the energy of the ultraviolet light is high enough that it can break the bonds between atoms and molecules in our bodies. And when it breaks those bonds, then you have potential to do damage. And so we worry about that. Your cell phone, by the way, its radiation is much lower in energy than the radiation of visible light. So generally, we don't consider it a danger, although we know that we can cook food with it. So if you have enough intensity, it can still be damaging just by heating stuff up. Okay, clearly I'm out of time. Have a good rest of the week. Remember, the test is on Friday. I will not be here. I'll be in California. The funeral is at 10 a.m., which is actually noon your time, but sure. All right.